Now we are going to see how we can design the arithmetic logic unit, or ALU. The main job of the CPU is to process the data or to perform some computations. And part of this computation will be performed by the ALU. Indeed, the arithmetic operations and logic operations will be performed by the ALU. We may have some shifting operations which will be done by the shifter. You can see here the block diagram that we are going to use for our arithmetic logic unit, ALU. We have two data input lines. The width of them is equal to n for both cases. So we have A and B. They could come from the register file. We have the function select input, the width of which is m, and therefore we can have up to 2 to the power of m functions to be selected using fs. And the result of the operation is made available as f, and obviously the width of it will be equal to n, which is the same as what we have for A and B. And there are also some status bits, we call them, as V, C, N, and Z. V will be equal to 1 when we have the signed overflow, C is the carryout, N is equal to 1 when the result is negative, and Z is equal to 1 when the result is 0. These status bits might be useful for some cases. For the arithmetic logic unit, we will consider the detailed design of typical ALUs and shifters. We will first focus on ALU and then consider the shifters later. For ALU, we will decompose it into an arithmetic circuit, a logic circuit, and then a selector to pick between these two circuits. First, we start with the arithmetic circuit design. For the arithmetic circuit design, we will decompose the circuit into an n-bit parallel adder. So we will have the n-bit parallel adder, and then we will have a block of logic which selects 4 choices for B input, okay, to the adder. Our adder will have 2 inputs. One input will come directly from A. The second one will come through a block of logic which selects 4 choices for B, as you can see over here. So this is the B input logic. We have 4 possible choices for B. So B is provided as one input to this B input logic, and then we have S0 and S1 in order to provide 4 possible cases as the output, or Y here. So one choice is to pass all 0, the other choice is to pass all 1s, next one is to pass B as it is, and the next one is to pass the 1's complement of B over here. Then the output that we get from our n-bit parallel adder will be available here as G. In any of those 4 cases, depending on the value that we have for C in, for the carry in, we will have G equal to A or A plus 1 or A plus B or A plus B plus 1, or it will be equal to A plus not B. Not B, indeed here is the 1's complement of B. Or we will have A plus 1's complement of B plus 1, or we may have A minus 1, and finally we would have G equal to A, depending on what we have for C in, whether it's equal to 0 or 1, and what we have for the second input, or the output that we get from B input logic. The data lines that we have will have the widths of n, obviously, again, for the input, 2 input lines and 1 output line. C in and C out will be in the form of a single bit. Over here you can see the all 4 possible combinations that we may have for S0 and S1, and in each case we will have a specific data appearing at the output of our B input logic. Let's go through it. So when S1 and S0 are equal to 0 and 0, as Y we have all zeros. Okay, Y is the output of the B input logic. When we have it, and when C in is also equal to 0, then G, the full adder that we have here, the n-bit parallel adder, will give us G equal to A. And then we will have transferring of data. If Cin is equal to 1, we will have A plus 1, or we have the micro operation of incrementing. When S1 and S0 are equal to 0 and 1, Y will be equal to B. Therefore, when Cin is equal to 0, we will have addition, A plus B. When Cin is equal to 1, we will have A plus B plus 1. So 1 will be also added over there. Later we will see whether it's useful or not. For S1 and S0, we have 1 and 0. 1's complement of B will be passed. Therefore, G will be equal to A plus 1's complement of B. For Cin equal to 0. For Cin equal to 1, we will have subtraction. Yeah? A plus 1's complement of B plus 1 is indeed equal to A minus 1. This is something that you should remember. And finally, when we have 1 and 1 for S1 and S0, the output will be all 1s. With Cin equal to 1, we will get G equal to A minus 1. This is something that may not be, let's say, that visible at the beginning, that clear at the beginning, why we have G equal to A minus 1, which is indeed decrementing. But if you try it, let's say we have 4 bits. If we are going to have A plus 1, 1, 1, 1, yeah? Then you look at plus 0, which is Cin. If you perform the addition and then you compare it with the decrementing, I'm sure that you will get it. Okay, I just let you to do it on your own. And finally, when we have Cin equal to 1 and all 1s, indeed we have A plus 1, 1, 1, 1 plus 1, this will be equal to A itself. We have 4 bits for A, so A is A3, A2, A1, A0, plus if we add these to each other, we will get 1, 0, 0, 0, 0. You can see that 4 bits are equal to 0 already. Therefore, if you neglect the carry out that we have, the output that we will get will be equal to A itself. So this is kind of easy to follow. The useful arithmetic functions are labeled already over here. So transferring here, incrementing, decrementing, addition, and subtraction are labeled. The other two which are not labeled aren't in the form of some standard useful arithmetic function. Something to keep in mind here is that for all 4 functions of B, for any of these 4 cases, we have at least one useful function or micro operations. This is something that we should also keep in mind.